There is a pattern in machine learning history. When we have compute that is limited, we add structure to how the machine learns. When we have compute that scales, we remove that structure. We have these early models that were tightly controlled. They had a lot of feature engineering built in and these handcrafted rules that allowed them to explicitly do their defined tasks. And we had an architecture that had separation. But as compute has increased, we've slowly started removing those constraints and letting scale discover this implicitly how these learn and what we can learn about learning from this as well. And transformers are really where this shift has taken place. And shown here, we can see that we've kind of started with the recurring neural networks. And with those neural networks, there was a lot of engineering hacks or tweaks in order to make these neural networks work for specific use cases. You can think of computer vision using these neural networks. There were specific hacks for specific events. So if you were doing something for a automated car driving sensor input, it would look very different than a security camera image capture for any sort of human detected. They had different engineering hacks in those different examples. And as we moved on to the transformers encoder and decoder style, that's really where we started to shift away from telling the models how to specifically learn and really let it determine the vectors of what the attention value should be. And decoder builds upon that as well, where it's got even less input from the encoder, but it still is able to successfully work very well for this model like a ChatGPT or many different models now are decoder based. And then now we're kind of moved into these agentic systems where we've got all these different models connected to different MCPs and tools that they can use in order to learn, do, and all kinds of cool things that are taking place currently. So, this original transformer was the encoder and decoder. What we had was we had our input tokenized, and then the encoder processed that entire sequence. It produced some contextual embeddings, and then the decoder had cross attention to the encoder's output. So it wasn't at the beginning stages, although there was different ways of trying to use encoder and decoder, and that has been done. But we used the output of the encoder that the decoder also looked over. And it worked really well for tasks like translation, where you had this short input and short output, and it could be graded very clearly since it was structured and there was clear boundaries about how these words are translated. But as this structure added complexity, we kind of had these cross attention blocks and there was separate stacks that were taking place from the encoder and decoder. And then there was this bidirectional encoding that took place where both had to work with each other. And it was a thing that really brought the need for scale in order for this to work well. So that's where we've kind of learned that when we're dealing with small scale, having more structure is helpful. Then we had something interesting with the decoder only. As this model scaled, the architecture outperformed the encoder and decoder system. So the decoder, what it really did was remove that cross attention that we previously talked about. And we had this separate encoder stack. And then our bidirectional encoding was also gone. So what it did is it just predicted the next token and it used a casual self-attention which is what this map of the visible versus masked showed. And it has this sort of triangular mask where each of the tokens can only see a previous token. So your first word only sees the one, your second sees the previous and then its current, etc., rather than seeing the future as well, which is what encoder model did. It showed both. So this really simplified the architecture. It gave it less structure, but as we scaled it more, it performed better. And that's the interesting thing about how the decoder only actually took over. And what we can see here is that there's really something deeper going on, that we're learning that these models, as they scale, they need less hand-designed structure. They need less rules. And at small scale, we find that the structure helps guide the learning. You can think of in the neural networks, you've got to give it the kind of handheld of how it needs to learn and what it needs to learn, like that reinforced learning. You need to have that in order to get the model somewhere. Otherwise, it just keeps guessing and it never actually builds any learning. And then at large scale, this freedom allows an emergence. So the model learns internal representations that simulate structure implicitly. It's actually learning the structure that we would have been teaching it. So we sort of stop forcing a intelligence or a rule set on the model and we let it discover how it should or what it should do by scaling. The problem is with doing that is you have to have a lot of compute. There's a ton of cost that comes with it. That attention scales in a n squared like function. That memory increases and then our computation explodes. So you need more architecture choices that are slowly becoming more of a system design choice so that the architecture can really flex its muscles, so to speak. What we've seen historically is that a sequence to sequence tasks has short outputs, things like translation, summarization, and classification. But now modern systems generate more tokens than they receive. Think about with ChatGPT, if you don't give it anything at all, it will go and give you a lot more information than what you initially put in. It's generative rather than explicit to a specific rule. You actually have to give it what you want the output to look like rather than it just going and giving whatever it thinks is best. So we can see that these decoder onlys have been really built around this generation. The shift really changes the latency, the token budgeting, the context management, and our caching strategy for the model because now it's got so much more that it's giving out based upon its input. That's why I'm tracking the output to input ratio in my system because generation is now the dominant driving factor in machine learning. So what we can see here is in this system, we can see that we're dealing with a decoder only because that's the architecture that is currently being used most in LLMs. And I built the inference server that has a self-refinement loop so that we can actually see the model trying to do better and better. We can see that there's an evaluation engine for it. We can see that it's got attention-aware metadata, and there's token tracking with the latency metrics. So when I run a request, we can see that we've got our context window, we've got our estimated attention operations, we've got our latency, output and input ratio, and then the refinement steps. So this really allows you to see those architecture decisions and how they're directly impacting your system behavior. We can see just given this simple prompt, very vague, right? But the model goes and gives this huge response comparatively. Some of this is garbage, right? It's kind of repeating, like we can see here, a feeling that we can all share, and then love is a feeling that we all share. It's very similar. It gives a lot of the same thing back, repeated. That's because we've just given it a basic input. We can see here under our evaluation, when we're doing something like explaining what the casual masking is and how that works, and this would be a general what a summarization is in 4 sentences. We can see based on our run evaluation that it's got a score, and we can actually add in more and more criteria in order for it to score on. But we've got our actual rationale here. We can see that it is, in fact, different than our answer, right? But it's got the same idea. It's got the same key elements to answer this question rather than up here above. We've really got a lot of weird garbage in here that isn't necessary. And that's because we've got a lot of tokens that it's outputting just because it can. So looking at this and how we have currently progressed, where are we moving towards? We talked about those agentic systems, but if we're following this pattern, as we're saying less structure, more scale, more ability for the models to do their own thing, then our next stage in machine learning is not going to be bigger models necessarily. It's going to be these systems around the models that allow the models to do more. And we're already seeing that with these agentic systems. In this architecture image, we can see that we've got the decoder only model. We've got things like RAG and agent tools and caching, logging and metrics, and then some evaluation. And what that allows is the system to grow more complex. It's not the transformer, but all of the stuff around the transformer that is allowing for more and more growth. We're already seeing this with things like OpenClaw, where you've got a model that essentially is just, hey, here's a bunch of tools. Go do whatever. You can go now do anything with these tools. That's really the key of the things that we are moving towards now. So I hope that you've learned something about the decoder only and how powerful it is and the reasons why it has done such a lot of heavy lifting in the transformer space. It really has changed a lot of the designing of systems, and it's really interesting to look at where things have been in order to see where things might be going. So as I continue to work on this system, there'll be more and more evaluation and metrics that are added to talk about the architecture and different ideas in transformers, but I'll leave those for another video.